In the last few lectures, we had been looking at factor analysis as a method of dimension reduction. So, what does the factor analysis do? It reduces the number of variables by consigning them to different factors, okay, which generally are smaller in number compared to the number of variables involved. Now, having done a factor analysis, what we have seen is that we can estimate the factor loadings and the variance components as well through either the principal component method or through the maximum likelihood method. Having done that, what is the next thing that we need to do? It's interesting to find out what individuals' factor scores are given the factor loadings and the variances. So, the question would be, given an individual's observation, can we find his factor scores? That is what we will be looking at today. We will be looking at two ways of doing that, finding the factor scores of a given individual, and after that what we will be looking at is an example which will illustrate the results we have been doing in the last few classes. In the last few lectures, we had been looking at the factor analysis model, where we had been estimating the factor loadings and the variances, particularly the communalities and the uniquenesses. Now, once we have fitted this model, a question of interest can be, what are the respective factor scores of given individuals? What do I mean by this? It means that we have used a sample data of say n individuals, and we have built our factor model, which is x is equal to mu plus LF plus epsilon. Okay. And we have estimated the parameters, primarily L, which are the loadings. So, we have got L hat, and we have also got an estimate for psi, which is basically the variance component. Now, once we have done this, can we in fact give the factor scores of each of the individuals? How would that help? Remember that originally each individual had m characteristics, and we have scores on this m characteristics. What we intended to do was to reduce this number of variables to a smaller set. Suppose we take only p of this factors. So, p is much smaller than m. So, we have reduced the m variables to p variable. What would be the scores of these individuals in terms of this p variables or the p factors? If I can find that, then instead of the m variables or m scores corresponding to each individual, we can now quote only this p score. So, we need to find the factor scores as such. Now, if you look at the model, x minus mu is equal to LF plus epsilon. L has been estimated. We have an idea of what epsilon is like. It's the error, and it has a dispersion matrix which we have also estimated. Mu again is estimated from x bar. So, can I find the factor f given all this? That would be the question. And there are two different methods of doing this. One would be the weighted least square method or the generalized least square method that we usually use in regression, and the other would be the other type of regression method where we start with the expected value, etc. Let me explain these two methods separately. First, the generalized least square method or the weighted least squares. Now, we have the model x minus mu is equal to LF plus epsilon. For the moment, assume that mu, L, etc. are known to us. Then what we have is, since epsilon has a dispersion matrix which is not spherical in the sense that the diagonal elements are different and different for each of the individual i's, therefore, we need to apply the weighted least square. And how do you do the weighted least squares? We minimize epsilon prime psi inverse epsilon, which really means that we minimize x minus mu minus LF prime psi inverse x minus mu minus LF. And if we take the derivative of this, it's easy to see that it becomes x minus mu minus LF prime psi inverse, and you get a L from the second half, the minus 2 multiplied to this. And when equated to 0, this would simplify to f hat being equal to L prime psi inverse L prime psi inverse x minus mu. So, given that we have already estimated L, mu and psi, our predicted factor score for a given individual with characteristics xi would be if I hat is equal to L hat prime psi hat inverse L hat whole thing inverse L hat prime psi hat inverse xi minus x bar. So, what we do is now, instead of the individuals xi vector which is m dimensional, we get the individuals factor scores which is the fi vector, fi hat vector which is p dimensional. And now we can summarize this. Instead of a larger set, we have a smaller set of variables to look at. There are certain simplifications we can always do, because remember, if we use the maximum likelihood method, L hat prime psi inverse L hat is equal to delta hat, the diagonal matrix. So, we can always put that in. That was the uniqueness condition that we had used there. So, we can make some simplifications, but the idea basically is that you need to do a weighted least squares to get the estimates. An alternative method is referred to as the regression method. Now, in this case, we start with the original factor model as x minus mu equal to LF plus epsilon, and we look at both x and f as random variables. Once we do that, remember that firstly x has a normal distribution with mean 0 and variance covariance matrix L prime plus psi. So, we assume that this is normal with the corresponding mean and variance. Similarly, we have f which is also distributed as normal, and remember we have assumed that f has a mean of 0 and a variance which is equal to I. So, if we take x minus mu and f together, then the joint distribution of this, now we have how many? M plus p variables, m of x minus mu and p from f. So, the joint distribution of this m plus p variables would be again normal with mean 0 and dispersion matrix given by sigma star. Sigma star, if you just partition it, it will have 4 components. The first component would be sigma, then you have L prime and I. So, the 2 block diagonals would be sigma and I, and the 2 off block diagonals would be L and L prime. So, if we use this results now remember again that this is a multivariate normal distribution, and if you remember the properties we have for multivariate normal distribution, you know that the conditional mean of f given x minus mu would be L prime sigma inverse x minus mu. That is basically the regression line. So, it is given by the covariance between f and x, which is L, and then the variance covariance of x, which is sigma, and that will come as an inverse, and then you have x minus mu. So, expectation of f given x is L prime sigma inverse x minus mu. What would be the covariance for this? So, the conditional variance covariance matrix for f would be I minus L prime sigma inverse L. Again, I is the covariance of f, L is the covariance between f and x, sigma is basically the variance covariance of the x matrix. So, it follows the usual result, and we get this as I minus L prime sigma inverse L. So, once we have done this, we predict the mean. So, instead of taking expectation of f, we substitute this by the f hat value. So, the f hat value now becomes, given the estimates of L, sigma, etc., f hat becomes, f hat is equal to L hat prime sigma hat inverse x minus x bar. So, for the ith individual given is xi, we get his factor scores as fi hat is equal to L hat prime sigma hat inverse xi minus x bar. Now, very often we can go from one to the other, that is, we can shift from the least square method, which we have done before, the generalized least square or the weighted least square method, to the regression type of method. So, this can be done through a very simple formula, which is L hat prime L hat prime plus psi hat inverse is equal to I plus L hat prime psi hat inverse L hat prime psi hat inverse. If we use this, we can show that the weighted least square estimates that we have found before are related to the regression estimates that we have found now through the relationship if I hat ls is equal to I plus L hat prime psi hat inverse fi for the regression method. So, these are certain ways of finding the factor scores. There are two distinct ways, and as we showed that these two can be related to each other. Next, let us look at an example. Now, to do that, we will go back and look at the same example that we did for the principal component method. So, in this case again, we have the track records of several countries, and this is for 8 different races, starting from the 100 meters, 200 meters to the marathon. So, some of them are short distance, some of them are long distance, and let us see if we can do a factor analysis on this and find out the factors which gives rise to this sort of results. Now, if we run a factor analysis model with this, and starting with all the how many factors we can have? We can have at most 8 factors. So, if we start with all the 8 factors, then we can run this regression and get a result which is shown here. And in this case, of course, we can do a rotation. We have, in this case, we have used the Varimax rotation. And what comes out is that if you look at the percentage of variance explained, you will find that the first factor explains about 47% of the total variability, whereas the second factor explains 45% about, the third factor 3%, and then on it goes smaller and smaller. So, the fourth factor is 1%, 1.4 in fact, and it becomes even smaller for the fifth, sixth, etc. So, we can safely say that if we take the first 2 factors, they together account for more than 90% of the variability. Well, if you are not satisfied, you can even go for the third factor, and they together would be very close to the 95% mark. So, we will be looking at only the first 2 or first 3 factors. In fact, if you look at the scree plot, which actually shows you the amount of variability explained by the factors, you will find that the first factor has explained the maximum of the variabilities very closely, followed by the second, and by the second we have explained almost 90%, and then it flattens out. Okay? So, in that case, we would be retaining 2 or at most 3 factors. Now, having done that, what are basically the factor loadings? The factor loadings, you can see for the first factor, it is 0.912 for 100 meters, 0.902 for the 200 meters, and so on and so forth, going to 0.476 for the 10,000 meters and 0.345 for the marathon. So, you can see that the loadings of the first factor are higher for the shorter races, whereas the loadings are much smaller for the longer races. Next, we go to factor 2, and now we see that the 100 meters has a factor loading of 0.369, 200 meters 0.385, whereas 5000 meters has 0.853, 10,000 0.851, and marathon 0.925. What does this mean? It means that now we have the second factor, which are more highly loaded towards the longer distance races. So, Of course, we need to talk to the experts about this, but this clearly indicates that there is some factor which influences the smaller races more and is not so influential for the longer races. Obviously, these results need to be interpreted by the expert, but what we can see is that in the shorter distance races, the first factor plays a major role, and for the longer races, the second factor plays a more positive role. So, suppose we call the first factor maybe the strength. You require more strength for the shorter distances. So, if you have more strength, probably you will be doing better in the shorter races. In the second one, you need more stamina, more endurance, and in this case probably the second factor is endurance, and the more endurance you have, the chances of doing better in the longer races is more. So, these two factors clearly distinguishes that the first races, the shorter ones, form one category requiring a different type of factor, whereas the last races form another category requiring a completely different type of factor. More interestingly, if you look at the third factor, okay, if you include the third factor, you see that this would be separating out, or it puts more weight on the 400 meters and the 800 meters. And what does this mean? It really means that this 400 meters, 800 meters have a separate entity of their own. It lies in between the shorter and the longer races, and probably it requires a little bit of both strength and endurance. So, it is a mixture of these two, and hence that comes out as a third factor if you want to include the third factor as well. Okay. So, it clearly tells you that there are certain underlying factors. It is not that these races are completely unrelated to each other, they have some common underlying factor, and it clearly distinguishes between the longer and the shorter formats. This is what factor analysis do, and what we can now do is that we can go back and do the factor scores for each of the countries. So, the factor scores for the first factor and the second factor we can do for Argentina, Australia, etc. So, what is F1 for Argentina and what is F2, and that will identify as to which country is good in which type of sports. That actually what factor analysis helps us to do, and that is how we can reduce a large number of variables to a much smaller one. In this case, from 8 variables to perhaps 2 or maybe 3 factors. In the last few lectures and in today's lecture, we had been looking at factor models. We have seen how you can build a factor model, we have seen how you can estimate the parameters of the model, and we have also seen how you can get the factor scores of individuals given their observations. So, what does the factor scores do? Basically, it can represent the individual's scores. Individual scores would be of higher dimension, the factor scores would be of a lower dimension, and then we have seen an application of this. So, as we have stated at the very onset, factor analysis is an alternative to principal component analysis. Both are methods of reducing the dimension of the variables. So, instead of looking at a large set of variables, we now look at a smaller set. We use the two different techniques according to the need of the data or according to what we actually are seeking. So, in certain cases principal component analysis is more relevant, and in certain cases factor analysis is more relevant, but both leads to the same goal of dimension reduction.